Okay, welcome to lecture. We'll get started here in just a second. We're picking up still chapter 19, radioactivity, nuclear chemistry. Okay, so last time we started talking about nuclear chemistry, and remember that nuclear reactions are different than sort of chemical reactions. One of the major differences that we were talking about was the idea that in a nuclear reaction, there's really no conservation of the elements. So that's very different than a traditional chemical reaction where we do have conservation of the elements, which is why when we balance a chemical reaction, we use those coefficients. And as we talked about, if you start with 4 carbons on the left-hand side, you should end with 4 carbons on the right-hand side. But here in a nuclear reactions, we actually change the subatomic particles that are found in the nucleus, our protons and our neutrons. And because we change our protons, which is the atomic number, that does change the elements. So there's really no conservation of elements. And that's why what we talked about was when we go to balance nuclear reactions, we balance them a little bit different than how we do our chemical reactions. We use the mass number on the left-hand side when we add up all the mass numbers on the left-hand side, which again are the top numbers that you see, top left of the symbol. When we add them all up on the left-hand side, they do need to equal everybody on the right-hand side in terms of the mass numbers. And the same thing for our atomic numbers, everybody on the left-hand side of the arrow. When you add up all the atomic numbers on the left-hand side, which are the bottom left of the symbol, we also need to make sure that it equals all the atomic numbers that we find on the right-hand side of the equation. So that's the way we kind of balance nuclear equations, is mass number, atomic number. And as we talked about last time, since the atomic number is the number of protons, and that is found on the periodic table, the atomic number, or the number of protons, is really what determines sort of the missing element, if you will. So in a lot of cases, you'll be trying to find sort of that missing element or nucleus, or really isotope, I guess is a better way of wording that. And the atomic number is really the thing that will allow you to do that. Remember that it may not necessarily be an isotope or an element that might be missing, but there might be a particle that might be on that side. And we saw several different types of particles. The common ones that we come across are alpha particles, which is basically like the helium nucleus. So sometimes they use the helium symbol or they use the alpha symbol. We have beta particles, which is like an electron. So they'll sometimes use the beta symbol or the E for an electron sort of symbol. There's also that positron, which has the exact same symbols as our beta particle, except that it is +1 instead of -1, like we find with the beta particles. We also have neutrons, which is 1 over 0 and n is used. Protons also particles that are used, either H for hydrogen, which is a proton, or P for proton is also used as well. So there's a lot of these different sort of symbols, including gamma, which is basically just pure energy, that are used in balancing these equations. So again, most important, right, when you go to balance these equations is you want to make sure that you have a periodic table. That obviously is extremely helpful when you're trying to balance these guys. And obviously the atomic number is really important. But most importantly as well is understanding the numbers that go with those different types of particles. So knowing that helium is 4 on top, 2 on the bottom, beta particles 0 and -1, because that's what's going to allow you to properly balance everything and make sure that you get to the right sort of missing element. A couple other things we talked about in terms of sort of reactions and nuclear reactions. Some words that are commonly used, again, if it's some type of emission or some type of particle has been emitted, or if it goes through some type of decay, that usually means that those particles will end up on the product side of the arrow. While if you have something that's been bombarded, say by a neutron or electron capture or something like that, then those guys typically will find themselves on the reactive side, those particles of the arrow. So probably most of the time you'll have the particle on the product side, but there are a few occasions, as we saw, that you can get the particle there on the reactant side. We also started, and I think finished here last time, sort of talking about stability and nuclear stability, and we use nuclear stability. One very common way that we calculate sort of that stability is what is known as that N to Z ratio. And that N to Z ratio is the neutrons to proton ratio. And we saw a graph, which I think if we come back here, a couple slides, we saw this graph here, which is what is sometimes referred to as the belt of stability or the valley of stability. And that's sort of a good ratio in terms of neutrons to protons for particular isotopes to be in. And it is sort of based on the atomic number. So 1 through 20, for example, if that's the atomic number, if anybody falls in that range, a good ratio would be 1. While if you get to like 20 to 40, 1.25 is a better ratio. 40 to 80, 1.5 is sort of a better ratio. As we talked about, there is sort of gray areas in between these cutoffs. But just as we talked about last time, for our particular class, we're just going to use them as pretty hard cutoffs just to make it a little bit easier in terms of determining is it really high or low, or is it in that grayish area. So for us, like on an exam or something like that, we'll use these as just really hard cutoffs. So either it is, for example, 1, or it's above 1 or below 1, and so forth. Now, if it's above or below 1, or which is really sort of as we have here with these arrows, you know, kind of too high or too low that ratio, what ends up happening is these guys will go through a decay process. And that decay process will move them closer to that belt of stability, may not put them exactly perfectly stable, but they should be moving sort of in the right direction. And for example, if the ratio is found to be too high, like we talked about last time, we will basically see the guy go through a beta decay, and that's going to bring it down towards that valley of stability. While if the opposite is true, if we have somebody that's a little bit too low in terms of that ratio, it will go through one of two types of processes. It could go through a positron emission, or it may go through an electron capture. And as we talked about last time, as we saw last time, regardless of which one you sort of choose there, in terms of positron emission or electron capture, it will end up being basically the same product that's being produced. So I think we looked at lithium last time, and no matter which way you did it, either electron capture or the positron emission, you end up with basically the same isotope at the end. And again, will not necessarily be perfect, although in this particular case that we looked at right at the end there, it was pretty perfect. We ended up getting a perfect ratio, but again, may not always be perfect, but you should see it move towards sort of the right direction in terms of that valley of stability or that belt of stability. And if you are asked a problem like this, again, you do not have to continuously sort of do it until you do hit that sort of stable ratio, but you definitely should at least do the first one if you're asked to write the equation, and that again should move you hopefully towards the right area. Any questions on that stuff we talked about last time? All right, so why don't you try one where we're at, I think. So why don't you give this one, a go here. Krypton 85, predict whether it's going to be stable. If it's not stable, then also predict what mode of decay will it go through, and why don't you write the equation for it. And krypton, in case you don't have a periodic table, there is 36 there. Is krypton on the periodic table. That would be its atomic number. So take a couple of minutes here and try to figure out A, is it going to be stable? And B, if it's not stable, which way it's going to go? And why don't you write the balanced nuclear equation for what's going to happen? And then we'll talk about it in a couple of minutes. Okay, so let's take a look. So we got krypton 85, and again from the periodic table, that 85 is the mass number, and then 36 would be our atomic number from the periodic table, which means our number of neutrons would be 85 minus 36, which should be 49. That also means that our neutron to proton ratio would be 49 divided by 36, going to give us a 1.36 as the ratio that we got going on here. So remember that krypton is 36, which again, if we go back here, 36 would put us in this range here between 20 and 40, which means an acceptable ratio would be 1.25. So coming back here, obviously, at a ratio of 1.36, we see that it is too high, our ratio, right? So since our ratio is too high, again, it will go through a decay process. And if our ratio is too high, it's going to go through a beta decay. And that means that if we were to write the reaction, it would be 85, 36 krypton. Going to do our beta decay, which again, you could use the beta symbol. You could use that E symbol if you like. And then now we need to balance out our atomic numbers. So I have 36 on the left. Again, because this is -1, I need to go one more, which takes me to 37. I then would go to 37, and that looks like RB perhaps. And in terms of our mass number, we would end up with 85. So again, because this is 36 and it falls into that region, we're looking for a good ratio of 1.25. So that is going to be, again, as we saw back here on this slide, maybe, or not. Let's see, what will change? There you go. As we saw on this slide, again, we're too high, so we're going to go through that beta decay. I'm just going to see it change on my slides. All right. So what does that mean? Again, this would be the product here that would be produced, our RB. And what we should see now is our RB should be moving in the right direction. So if we now take for our RB, 85 minus 37, we'll grab the calculator here. That's going to be 48 neutrons divided by 37 protons. We're now at, we'll call it 1.3-ish. And again, this illustrates to you what I was saying earlier. It may not perfectly hit that ratio. Remember, 1.25 was a good ratio here. But we started at 1.36, which was higher. But now we've moved the least down to 130 or 1.30, and we're at least heading in the right direction downward to that more acceptable ratio. Any questions on that there? So this is a very good way to look at stability. There are some other ways that we look at stability. So let's take a look. There are some magic numbers, perhaps. So besides sort of that N to Z ratio, which is sort of a good way to look at stability, another important way is to look at the number of protons and neutrons. Not necessarily the number of protons and neutrons, but whether or not they are an even number or an odd number. So when we look at this table at the bottom, which again is not from your book, but you have a very similar table in your book. When we see that we end up with an even number of protons and neutrons, that's sort of the best situation in terms of stability. You can see there's about 157 stable isotopes that have that arrangement, sort of positive and positive, or not positive, really even and even is a better way. The next sort of best situation is still even number of protons and odd number of neutrons. So you got about 53. You see a dramatic sort of drop in stability there as we go down. The third sort of best situation would be odd protons, even neutrons. And as you can see here, sort of the worst situation of stability, if you're just kind of quickly looking at stability, is if you see you have something that has both a odd number of protons and a odd number of neutrons. Very good chance that it's probably not very stable, that isotope there. And as you can see, there's only about 5 naturally occurring stable nuclides that are like that. Also, if you add up the total number of nucleons, and by the way, nucleons, just so we're clear, much like the name almost implies there, is pretty much what makes up the nucleus. So here, that is your protons and your neutrons. So that's a common word that you hear a lot in nuclear chemistry, is nucleons, and is basically the particles that make up the nucleus, which hopefully, as we know, is the protons and neutrons. It's really the mass number, right? So the mass number is protons and neutrons. So that's sort of what nucleons are. And if we add up the total number of nucleons and it adds up to one of these sort of magic numbers, it's kind of like when we do electron configuration, how everybody's trying to get to noble gas configuration. It's kind of a similar situation. So things are most stable when either N or Z has a number of 2, 8, 20, 28, 50, 82. And your Powerball number there is 126, or the number of neutrons would be 126 in that case. So in terms of stability, if you could do it, probably calculating the N to Z ratio is a really good way of looking at stability. We'll also see as well a little bit later here, calculating something that's known as nuclear binding energy is another good way to look at stability. You know, probably, again, this sort of table here is it's a good way, you know, to sort of kind of quickly maybe figure out stability. But if you can, probably the calculation-based way, one of those sort of calculations is probably your best sort of approach. Any questions on stability there? Okay. So let's then talk about a decay series. And in a decay series, it basically is what it sounds like. You have an isotope that is not very stable, and it will continue through a decay process, basically sort of one reaction after another, until it finally is able to basically hit something that is stable, and then it will sort of stop. And I'll get to your question in just a sec, okay? So in a decay series, we have these sort of series of steps that we follow, and we continue until we do hit something that basically is stable. And there's a couple of different ways you could sort of figure out what's happening with your sort of decay series, or figure out what's being produced. So one way you can sort of figure something out is to take every alpha decay that you have. So for every alpha decay that you have there, from the mass number, which is our guy up on top. So from our mass number, we want to subtract 4 from the top. And from the atomic number, we want to subtract 2 from the bottom. And then for every beta decay that we do, we want to add 1 back to our atomic number there. So if you're really just sort of interested in the end result, you could kind of use these kind of quickly to figure out, you know, what you're going to get at the end. You also could do it by doing sort of individual nuclear reactions or equations like we did before. So let's just say we had uranium 238. And again, let's say it went through an alpha, alpha, beta, beta, alpha sort of decay series. We'll just pretend it stops there. And you wanted to know basically what you would get after each of those sort of processes, or maybe what you would get at the end. So if you want to kind of do it and maybe not worry about misadding or something like that, the best way to do it is just to do it like we were doing with our nuclear equations. So the first thing it's going to go through is an alpha decay, which means we would write an equation just like we did before. That means after this first step, we would have 90 for our atomic number, and up on top there would be 234. We would go to periodic table and see number 90 is TH. Then what would happen is the 23490 would go through an alpha decay, which means our particle would be over here. And we would end up with 88, I believe, and 230 there on top. And again, 88, which is the atomic number. If I go to my periodic table, hunt it down there somewhere, RA, looks like. Now what's going to happen is that RA will then go through a beta decay. So we'll go to 30, 88 RA through our beta decay. That's going to get us to 89 and 230. And again, 89 would be AC. Then our AC will go through a beta decay. And just got to move some stuff here. Drop that down. There we go. So next would happen would be 23089. Goes through one more beta decay here. And again, we're going to have to go up now to 90 and 230. And 90 again brings us back to TH. And the last thing that will happen is our TH there will go through a alpha decay, which is going to get us to, I believe, 88. And a lot of math there, but 226, I hope. And 88 again brings us back to RA. So if you have this sort of decay series and you want to find out what you get after each step, you could just do our nuclear equations just like we did previously. And as you can see here, essentially what's happening is the product of the first decay series then becomes the reactant in the next one. So this again is like your parent, and this is your daughter, then the daughter becomes the parent, and then the daughter, and so forth as you continue down. Now, if you weren't necessarily interested in the entire thing there, but you just wanted to figure out what's going on at the end, you could do sort of the mathematical approach. So we started basically with 238 and 92. We had 1, 2, 3 alpha decays, which means from the top, -4, -4, -4 is what we should take off. We also had our 3 alpha decays, which means -2, -2, -2 from the bottom. And we had 2 beta decays, which means we should add 1 and 1 back to the bottom. So again, if we do that math, we're down to 238 minus 4 is 234. 234 minus 4 is 230. And 230 minus 4 gets us to our 226. So we got a top. 92 minus 2 is 90. Minus 2 more is 88. Minus 2 more is 86. Plus 1 and plus 1 is 88. And you can, get to the end result by, again, doing that sort of mathematical approach. So if you're not necessarily interested in every single step along the way, you just want to get to the end there, you could kind of do that mathematical approach there and sort of figure it out relatively quick. Or again, you could do it individually and not worry about it and use that to sort of check to make sure that you did it okay. Any questions on that? Okay. And here is sort of that decay process for uranium-238. And again, you could kind of see it continues to decay. It actually will sometimes split off into sort of 2 separate pathways here. in terms of it, but eventually we'll all sort of end up in sort of the same situation, and it'll end up with that more stable isotope being reached there at the bottom, which in this case was lead 206 at the end. So what we're going to talk now about is kinetics of radioactive decay. And all radioactive decay will basically follow first order kinetics. And if you're familiar with first order kinetics, and if not, we'll talk about at the very end of this sort of semester. First order kinetics and kinetics really deals with how fast or slow a reaction takes place. But first order kinetics really has two rate laws, which are sometimes referred to as the integrated rate laws, and that's the natural log of A equals the natural log of A naught minus KT. And the half-life, which is the time it takes for half of whatever you started with basically to go away. So if you started with 10, after the first half-life, you got 5. After the second half-life, you got 2.5, and so forth. That's basically the half-life. Now, in sort of chemical kinetics, when we use first order sort of rate laws, we usually use concentrations. But in nuclear chemistry, we oftentimes will use grams, for example, milligrams. We will also sometimes use rates. So you could use a rate in there of radioactive decay, and we'll see some of that in just a second. Now, a couple of things that are slightly different, even though they're really this sort of the same thing. Sometimes in nuclear chemistry, this guy here is what's known as the decay constant. And in regular kinetics, that's what's known as the rate constant. It's the exact same deal. And because it's nuclear chemistry, some people will even use the lambda symbol to represent the nuclear decay constant. So you'll even actually see that little lambda symbol sort of used for it as well. And as you can see here, they don't necessarily use concentration like molarity, but they use N, and N stands for nuclide. So beginning nuclide or, sort of ending nuclide is what those stand for. And as I mentioned before, instead of sort of concentrations, people will also sometimes use rates as well. The T here, just so we're clear, this is basically time, yeah, not temperature, so that is time. And half-life here, that's half the time it takes for, again, you to lose what you started with. Natural log of 2, which is 0.693, if you type that on your calculator, equals K. This is what we can use to help us determine the changes in sort of concentration, if you will, over a period of time. And there is also a graph that usually goes with our first order kinetics, and that is the natural log of A versus time gives you a straight line where the slope equals the rate constant or the negative decay constant. 0.693 is what you get when you take the natural log of 2 on your calculator. So you'll sometimes see 0.693 used instead. So if you take natural log of 2 and hit equals, you should get something like 0.693. Other question on that. So these two equations here are used a lot together. So a lot of times you do have to use sort of the half-life equation and this equation together to solve what you're looking for. And in most cases, what you're missing is the decay constant. So you have to use the half-life to get the decay constant and then use the top equation to figure out whatever you're looking for, rate, concentration, time, or something of that nature. So sometimes when you go into this top equation, you have like all the information except for the decay constant, and usually you'll have to use the half-life equation to do that. So here's the two graphs that are associated with first order. If you take just the concentration versus time, you'll have this decreasing with time graph that we usually will see. And again, this is our more y equals mx plus b type graph, where we rearrange this guy with the natural log of n equals the natural log of n naught minus, as you can see here, they use the lambda. And this is another symbol, like I said, for the decay constant. Sometimes nuclear chemists like to use their own symbols, makes them feel good, I suppose. But I'll use K plus that, plus the natural log of N naught. And this is Y is equal to mx plus B, basically. And that gives us our straight line there. So you can see on the Y, we have our natural log of N, or A, if you like to use A. And on the X, we have the Y. And again, our slope equals minus K when we look at it. So these are some half-lives of some different nuclides. And you can see, not everything is super quick. Some half-lives, for example, uranium-238 is 4.5 times 10 to the 9 years, which means none of us will be around to see one half-life, I don't think, unfortunately. You can see carbon-14 is 5730 in terms of their half-lives. But some things are quick. Obviously, Rn-220, 55 seconds or so, 56 seconds. Usually about after 10 half-lives, it's pretty much gone, right? Go about 10 half-lives, that's almost 100% of it. Usually we'll have most of it gone. So let's take a look at a problem here. And I'll give a chance here to make sure. So why don't you try this? If you started with 1.35 milligrams of plutonium-236, how much will remain after 5 years? Here's some information for plutonium. 2.86 years is the half-life. Again, try to use that first order equation we just saw and see what you come up with, and then we'll talk about it in a couple of minutes here. Okay, so let's take a look at this one. So again, as soon as you see anything that involves sort of kinetics or anything like that, uh, it is going to involve that first order. So what that really means is those are the two equations that we saw. I'll just use more of the kinetics one. Natural log of A equals natural log of A naught minus KT. And again, just so we're clear that first A is sort of like your final concentration, if you want to think about it. The first A over here, which has the naught that I missed, is your initial kind of concentration. And again, the K here is decay constant when you're doing chemical kinetics, but our decay constant here in nuclear kinetics. And again, T is time. And again, that goes with our half-life equation, which is a natural log of 2 over K. So in this case, we're looking for how much will remain at the end of 5 years. So really, when we look at this equation, we are looking for this guy over here. We have the initial, which is 1.35 milligrams. We have the years, which is 5 years. So you can see this is what I was talking about before. We are missing one important piece of information, which is the decay constant. And that is where the half-life comes into play, because we know that the half-life equals the natural log of 2 over K, which means that the decay constant would be natural log of 2 divided by the half-life, which would give us a natural log of 2 divided by 2.86 years. And if we do that, we get something like 0. We'll call it 242. The units here are actually reciprocal years. And that also is really important because a couple of things. First order kinetics, the units of the rate constant is usually 1 over seconds or 1 over some unit of time. So 1 over year would fall in that category, okay? The other thing that you also want to watch out for when you use these equations is these two values here. You do want to make sure that they are in the same unit of time. In this case, I got 1 over years, and I have 5 years, so I'm good in that case. But sometimes very common, the K and the T, one might be, say, in years, one might be in days, one could be in weeks, one could be in hours, minutes, seconds. So there's a lot of times you got to make sure that these two guys over here, the K and the T, they are in the same unit of time. Does it really matter what unit? Not usually, as long as they are the same, but they do definitely need to be the same. So we have pretty much everything we need now. We could take the natural log of A, which is what we're looking for, would equal the natural log of our initial, which is 1.35, minus our 0.242 years. And I kind of ran out of room, so I'll go this way. Times our 5 years. Yeah. So the years will cancel, which is good. So if we clean up the right-hand side there, we're going to take 0.242 times 5. We're going to take the natural log of 1.35 minus that number. And it looks like we end up with the natural log of A equals minus 0.91169. To get rid of the natural log, we need to take E of both sides. We take the E of that and the E of this. That will give us that A equals 0.402. And the units here would be the same units as what we started with. So these would be milligrams in this case. A couple of things on that. It should make sense in the sense that we ended up with something that is less than what we started with, since it's going through a decay cycle. If we ended up with more than what we started with, that probably would not be good. So it should be going down as we go through here. Any questions on that? It roughly did just under 2 half-lives, right? So if you roughly did 2 half-lives by taking 1.35 divided by 2, you get 0.33. This is obviously less than 2 half-life, so you should have a little bit more. So 0.402 would sort of make sense. Any questions on any of those calculations there? Okay. So why don't you try this one here, Radon 222. It goes through decay. If we started with 10.24 grams of it, how much will be there in 5.4 weeks? So there you go. Let me see. I think you might need a number that got lost somewhere. Let me try and find that number for you. The half-life of radon is 3.8 days. Oh, it's right here, actually. It did not get lost. It's right there. Perfect. That's all you need, I think. All right, take a couple of minutes and give it a go. See what you come up with. Okay, so let us take a look at this one here. So same idea. Again, anytime you're sort of interested in sort of time and concentrations going on, we're going to use our first order, which is our, again, natural log of A equals natural log A naught minus KT with our half-life to help us out if we need. So same idea here. We're looking for our final, which again is this guy. We do have our initial, which is the 10.24. We're going at 5.4 weeks. So just like the last one, and very, very common, we're missing that decay constant. So that is where the half-life would come into play. So we do have the half-life here, which was 3.8 days. Now, we do want to think about sort of these two units as we were talking about. The time, which is this guy, it's in weeks, and obviously our half-life's in days. So you do need to do a conversion. It truly doesn't matter sort of which one you convert, but I'm going to convert the days into weeks. So I'm going to do it that way. If you chose to do it sort of the other way, take the weeks into days, you may get some slightly different numbers until the end. You should get the same number, obviously, at the end. So there are 7 days, right, in a week, I think, still. There we go. So 3.8 divided by 7 gives us 0.525429 weeks. So I'm going to go into my half-life equation with that number there. So my decay constant would be the natural log of 2 divided by the half-life, rearranging the equation up here. And that would give me natural log of 2 divided by 0.5429 weeks. And if I do that, natural log of 2 divided by 0.5429 gives me 1.277. Again, the units here are reciprocal weeks, 1 over weeks. So now we got everything we need to go into our equation. Natural log of A equals the natural log of our initial, which was 10.24 grams, minus our 1.277 weeks, 1 over weeks. And that works good because our time is 5.4 weeks. So here again, you want to make sure that these are the same units, so everything cancels. Again, you could have went days on both as well. It should all come out the same in the end. So 1.22 times 5.4, natural log of 10.24 minus, should be 6.89, gives us the natural log of A equals minus 4.568-ish. We're going to take the E of both sides. That's going to give us E of this guy up here. And looks like if we do that, we'll call it 0.010. And the units here would be grams, just like the original units, right? Give or take. Any questions on that particular one there? And again, if you converted it to days, you should in the end get about the same number. It also has obviously gone down, which is good. Again, pretty much we've gone through a number of half-lives at this point, so it should have gone down by a bunch. Any questions on any of that stuff? So as you can see, unlike sort of traditional chemical kinetics, if you've done kinetics before, again, we're going to talk about kinetics at the end of this semester, but usually in kinetics, we use molarity in there. We'll sometimes use maybe pressure, but usually molarity. But here you can use anything like you see here, grams, milligrams, or even some counts, as we will see. Any questions on kinetics here? So another application that we could use kinetics in sort of radioactivity is in the case of sort of radiocarbon dating, or figuring out really how old something is, for example. Um, so for example, here we could do some carbon-14 dating, and our carbon-14 dating will tell us, how old something is. And if you do see it has anything to do with carbon and sort of radio dating, here's the half-life for carbon that you would want to use, which is 5730. You can also do some uranium-238 dating and sort of figure out how much lead is produced. And the half-life for that is 4.51 times 10 to the 9. Sometimes we do products minus reactants there to figure out sort of the difference in the amount of products that's produced versus where we started with. So this is one that comes up a lot. Carbon dating is used a lot. So that, again, that half-life of 5730 is used a lot. So let's take a look at one here and sort of see if we have an ancient skull that gives us 4.5 DIS/MnGC. If a living organism gives us 15.3, how old is the skull? You may say, well, that's a lot of words right there. So what is all of this? So let's talk about what that basically is. That is basically a unit of radioactive decay. And what that means is disintegrations per minute. So that's what the DIS/MIN is disintegrations per minute. The G is actually grams, and the C there is not Celsius, like a lot of people think, but it is actually carbon. So that is disintegrations per minute per gram of carbon. So why would per gram of carbon be important? It would be important because of this. I know we're dealing with carbon. I know this should be my half-life that I am dealing with when I'm going to do that. So this is really just, again, a radioactive decay problem, a kinetics problem, but we're going to use rates instead of grams, milligrams, or something like this. So how that works is pretty much just like what we did before. We're going to use our two equations, really, that sort of tie into our first order kinetics. And again, our half-life is equal to the natural log of 2 divided by k. And in this case, we're looking for, we have an ancient skull and we have a living one. So much like in life, right, we live first. So that's our starting. And then we don't live so much at the end of our life there, right? So that is our ending there, right? So obviously the ancient skull is the final. The living is sort of the beginning. That means that we are looking for time in this case, how old it is. So just like previously, we are still missing the decay constant. So again, that's why it's important to know that it is grams of carbon, so that we will go back and use obviously our 5730 as our half-life. So we know because it's per gram of carbon, the half-life is 5730 years. So that's going to allow us to figure out, much like we did a number of times at this point, our decay constant by taking the natural log of 2 divided by the half-life. Gives us the natural log of 2 divided by 5730 years. And gets us something like 0.0000. Did I do too many zeros? I did. 121. Too many zeros there. Just get rid of that. All right, so 121 units here, again, going to be reciprocal years, which is okay in this case. It just means when we solve for the answer, we're going to be in years. So at this point, we have everything that we need. We're going to take the natural log of our final disintegrations per minute, which is 4.5, equals our initial, which is 15.3. By the way, this number here is larger than this number here, again, because that's our initial, so it should be giving off lots of radioactivity. And as it starts going through half-life, there's going to be less and less radioactivity happening, which means we're going to have less in terms of sort of a rate of radioactive decay. Minus our K, which we just calculated. And we're going to actually solve for T in this case. Yeah, so something like that, the half-lives will be given to you. The formulas won't like normal, so you do need to know, obviously, the natural log of A equals natural log of A naught minus KT and those guys. But any type of half-lives would be given to you, unless obviously you were asked to solve for a half-life. But, obviously, if you needed it for a problem, it would be given to you. So at this point, we could clean up some stuff here. What I'm going to do is take the natural log of 4.5. I'm then going to subtract it from the natural log of 15.3. So I'm basically taking this guy to the other side, right, and subtracting it. That gives me minus 1.223775 equals minus 0.000121 years divided by T. I'm going to divide that to the other side, the 0.000121. And that is going to give me a time that is 10114 years and probably about 3 significant figures maybe. So 10100 years. So that is, 10,000 years old. Kind of makes sense, I suppose. I guess that's ancient for sure. Any question on that calculation? So very much like the other ones we're doing, except here you can use something like some type of unit of radioactive decay, like in this case, disintegrations per minute per gram of carbon. Any questions on that? All right, so why don't you try one then yourself? Oops. So we have civilization about 15,600 years ago. If a living sample of rice, I think it is, right? Gives 20 counts per minute per gram of carbon. What is the counts per minute per gram of carbon if you found a piece of rice on that site? So see what you come up with. And again, a hint here, since it is still carbon, you would use the last half-life, the same one. Okay, so let's see how we're doing. So same thing that we've been doing. Again, this is just a different sort of unit of radioactive decay. So before we saw disintegrations per minute, counts per minute. It's another very common one. And again, counts per minute per gram of carbon is what that C stands for. So again, that basically tells us that we are using our same 5730 as our half-life, just like we did over here in our previous problem. So if we look at our formula, natural log of A equals natural log of A naught minus KT. We're looking for the final counts per minute, which would be this guy over here. We have our initial. We know they were going 15,600 years. So just like previously, and very, very common that you have to use that half-life equation. So I'm not going to recalculate it because it will come out the exact same as what we had on the previous slide. And we will get 0.000121 as our decay constant. Again, the exact same calculation as what we did on the previous problem will get us there. So that means that I have the natural log of A, which is what I'm looking for, equals the natural log of our initial counts per minute, which is 20, minus our decay constant that we calculated last time, which again will be the exact same as it was here, and 15,600 years. In this case, again, our time is okay because they are both in years. Not always the case, so you want to watch out for that to make sure that they are the same units. And if we kind of clean up the right-hand side there, we get 0.000121 times 15,600. We're going to take the natural log of 20 and subtract that. And it looks like we end up with the natural log of A equals 1.108 in this case. Again, to get rid of this, we're going to take the E of both sides, and that will give us our final answer here, which would be about 3.03. And if you're interested in what the units would be, it would be the exact same units as what this first one was. So this would be counts per minute per gram of carbon. Also does make sense. Again, this is going through a decay process, which means after 15,600 years, that's at least 3-ish half-lives, a little less than that. So again, should be less radioactive, and because it's less radioactive, should be giving off less decay or counts per minute. So our counts went down, which does make sense in this case. Any question on that calculation? So like I said, you do need to know these kinetics ones. It's always first order, which will make it easier when we get to kinetics, chemical kinetics at the end of the semester. You'll see these exact same formulas again. We'll just kind of apply them a little bit differently, but kind of similar. The only difference is we'll use molarity in most cases instead of sort of grams or counts per minute, but it works pretty much the same way. Any questions on that? Okay, so the next thing we're going to talk about then is where does the energy of fission come from? Good talk. Let's talk a little bit more about that maybe. So fission, again, a reminder, is it's a process where it can spontaneously happen that you have a unstable nucleus that essentially will split off into, so you could have this unstable, I'll draw it like this, unstable nucleus that will split off into some new nucleuses. Usually will give off some neutrons along the way, and it also will give off usually a lot of energy along the way. So where does this energy sort of come from? It comes from sort of the difference in the particles that make up the nucleus and the atomic mass of that isotope. So remember that the nucleus is made up of those protons and neutrons, which is a nucleon that we talked about. And there's a slight difference in mass between basically the mass of those particles as you put them together and the mass of the actual isotope. And that slight difference in mass is what gets converted into energy through the process of fission. And it is done through, one way you could calculate it is using Einstein's equation, and that is E equals mc squared, where c is our speed of light, 3 times 10 to the 8 meters per second. M in this case is mass, but it was also known really as, in this application, the mass defect. And the mass defect is that difference in mass of the particles that make up the nucleus and the actual atomic mass of the isotope. So it's that slight difference in mass that through a process kind of gets converted into energy when this happens. Now, as we talked about, a uranium-235, for example, when it goes through fission, produces about 1.7 times 10 to the 13 joules of energy. And if you compare that to some type of exothermic reaction, exothermic, right, giving off heat and energy, produces 10 to the 6 joules per mole. So you got almost twice as much energy coming out from a fission product, a reaction, than you do in your most sort of exothermic type reaction. And the difference because of that is because we are changing in nuclear reactions, those protons and neutrons, they're being changed into neutrons, protons to neutrons, neutrons to protons, and so forth. And obviously that takes a tremendous amount of energy to start changing those nuclear components, as opposed to an electrical reaction. In a chemical reaction, we just deal with the electrons, which are on the outside. It doesn't take as much energy change that occurs. So there definitely is that sort of big difference in energy that occurs when we do that. So that brings us to the idea of what's known as mass defect and the binding energy, for example, and sometimes referred to as nuclear binding energy. So when a nucleus basically forms, the mass of those separate nucleons is converted into energy, and there's that slight difference that occurs between the nucleons when they combine and basically the mass of the isotope. And again, as I mentioned before, that's basically what is known as the mass defect. Now, there's a couple ways you could sort of calculate the energy associated with it. You could use Einstein's equation. You could also, if you want, use these sort of conversion factors here, which also truly do come from Einstein's equation. But sometimes people will just use these and not really think about Einstein's equation. And I'll show you an example in just a second of doing it sort of both ways, and you'll get the same answer depending on which way you want to do it. But 1 mega electron volt, which is a common unit, mega electron volt, common unit of nuclear bonding energy, equals 1.602 times 10 to the minus 13 joules. And again, joules obviously is also a very common unit of nuclear binding energy. So mega electron volts and joules are two very common units that are used to express the binding energy that's occurring. Now, why is binding energy sort of important? When you calculate the binding energy per nucleon, the higher the number, the more stable that isotope is. So this is another way that people could kind of look at stability, is to calculate the actual binding energy. And the higher the binding energy per nucleon, the more stable that isotope will be. So let's take a look at an example here to kind of show you two ways to do it. All right, so if we take, oops, we'll do this guy here. We'll just see where that number I was looking for, 189984. All right, 189984 AMU. So let's say we took our fluorine-19 nucleus, and it had an atomic mass of 18.9984 AMU. Put the U there. And we want to calculate the binding energy. So the first thing that we want to do is figure out the mass of the particles that make it up. So in this particular case, if we took 19, which is the mass number, minus 9, which is the atomic number, that tells us we have 10 neutrons. Also, we know it has 9 protons. So to find the mass defect, we would want to take the mass of those 9 protons, and the mass of a proton is 1.00 7825, and that would be provided to you. Plus are the mass of our 10 neutrons, and the mass of a neutron is 1.008665. And then we would subtract it from the atomic mass of that isotope, which is 18.9984 AMU. And if we do that, we get a difference of 0.1586 AMU. This is what is known as the mass defect. That is the difference between the mass of the particles that make up the nucleus and the actual atomic mass of that isotope. That is the mass that's going to be kind of converted into energy through this process. So if we wanted to calculate the binding energy, we could take E is equal to mc squared. If we want to do Einstein's equation, this mass defect would be our mass. We would times it by 3 times 10 to the 8 meters per second, which is the speed of light, that's c. And if we do that, that gives us 1.428 times 10 to the 16. The units that we're in at this moment is AMU meter squared second square. Now, perhaps you remember a while back at some point in your chemistry career that if you have a kilogram times a meter squared divided by second squared, that is the same as a joule. So we would want to take this number and actually get rid of the AMU and convert it into kilograms. And to do that conversion, there are 6.022 times 10 to the 26 AMU in a kilogram. That number also should look familiar to you. That is our good friend Avogadro's number, except that Avogadro's number is to the 23rd, and that would give you grams. But here we want kilograms, so that's why we're to the 26th here. And that gives us 2.37 times 10 to the minus 11 kilograms meter squared second squared, which is the same as a joule. So the binding energy here is 2.37 times 10 to the minus 11 joules. And usually the way binding energy is displayed is by taking that number and dividing it by the number of nucleons, which in this case is the mass number, or 19. And if we do that, we end up with 1.25 times 10 to the minus 12 joules per nucleon as the binding energy for this particular guy. Now, that is one common sort of unit that is used to represent binding energy, which is joules per nucleon. And if you remember, I told you you could kind of avoid using Einstein's equation and just use those two conversion factors that we have here. So just to show you that, we take the AMU that we got up here, which was 0.1586 AMU. We could use that, as we see back here, there's 931.5 mega electron volts per AMU. And that's going to get us 0.1586 times 931.5, 147.7. And if we want to use our joule conversion, 1.602 to the minus 13. We will get, as you can see, hopefully the exact same number as we had previously, that 2.37 to the minus 11. Which is this number right here, which at that point we could obviously continue it up the other way and divide by 19, which will give us the exact same number. So if you want to use those two conversions, it really is the same thing as using Einstein's equation and doing a little conversion with Avogadro's number. And you can see they both really do get you to sort of the same sort of spot. So we can use nuclear binding energy per nucleon as a measure of stability. Again, the higher that number, the more stable it is. Any questions on that? Obviously, I could finish that one up by dividing by 19, like I said, and you'll end up with the exact same thing I had boxed on the left-hand side. Okay, we will stop there today. We're almost pretty much done with this chapter. It's got another example or so to go and a couple other things to talk about, but we're pretty much there almost. So we are off to lab. We'll start lab about, we'll start 10 after, take a little break to stand and stretch since we went a little long here with lecture. And we are doing experiment. I want to say 10 sounds kind of familiar. It is experiment number 10. So 10 and 11 do go together. So 10 today, 11 tomorrow, and they're kind of related to each other. So I'll see everybody in about 15 minutes. We'll do 10 after, come through the lab lecture. And before we take off though, hang on one sec. Actually, you know what, I'll talk to everybody when we get to lab about it. That's the start of lab, we'll talk about it. Okay, I'll see everybody in about 15 minutes. Make sure you hit here if you didn't do so already.